Today, what I'm going to talk about, in some senses, is not directly relevant to any particular lab that you've done, but it's a very, very important topic, and that is it's confocal microscopy. And it, in fact, is a direct extension of the 2D microscopy that we've talked about. That is, ordinarily you find that in X and Y you can resolve things, and in Z it's much more difficult. When we have the ability to look at single molecules, you can get X and Y very well. You can get both the accuracy and the resolution. And the difference, again, with Fiona is basically that the fluorophore will put out enough photons. And in that super accuracy, for super resolution, what is it that the fluorophores need to have? That's right, that they're photoactivatable, or they blink in terms of turning on and turning off. Also, they must have reasonable photostability in terms of, ultimately, you want them to give enough photons such that you can resolve it reasonably well. Okay, and finally, we talked about this last time, is you can get not only very good X and Y accuracy or resolution, but in fact, you can also get the Z dimension. And you get that via a trick in that you put a cylindrical lens beyond the objective, and what you have is, if the Z is 0, you're directly in plane, it basically looks normal. If the Z-axis is below the plane, then what happens is, in one direction, in this direction called the Y, it becomes elongated, and the X essentially is not changed. So by determining the ratio of X to Y, you can get the Z-axis out of it. So you determine the center in terms of X and Y, and you determine the ellipticity, essentially, in Z. Yes?
So for this, in order to get this three-dimensional image of a single dye, the dye has to move, or the stage has to move?
No.
Then I don't understand.
Okay. Why do you think that this stage has to move?
Because it has to get out of focus.
In fact, that's right. If it's in focus, it looks like that. Then,
it has to get out of focus to get the three-dimensional.
well, no. Here you find it's so-called in focus. The X and the Y is equal to each other. So you call that is Z equals 0. Okay? Now, let's say, so you have Z equals 0 over here, and let's say then you have another molecule which happens to be over here. Okay? In that case, the X and the image that you form will be something like this. It'll be, the X and Y will be over a certain amount, and the Z, it's not moving, but the x and the y will no longer be equal.
But for the molecule that's at 0, if it's in focus, we get only two-dimensional image, unless we have the calibration.
Oh, absolutely. You need the calibration such that, you can say if the y-axis is, this distance across, and the x-axis is that distance across. So
when we did microscope experiments at the very beginning, we talked about DIC and phase contrast.
yes.
So for example, in DIC, we use the interferometer. So with an I was thinking about that. So with an interferometer, could we get a three-dimensional image of the same dye in focus at 0 to get it out of focus and then in what direction?
Okay.
Moving? Or is that...
Okay, you're talking about, like in this case, DIC and phase contrast. So those are primarily, well, not primarily, they're exclusively ensemble measurements. You're not taking a single molecule. So it doesn't work. Okay. Any other questions? Okay. So now, this is just showing that it is working at the single molecule. Oh, no. I don't know. This is supposed to spin around. I showed it to you last time. Sorry about that. But you can see at each point you get X, Y, and Z, and therefore you can, afterwards rotate it around so you can see. That happens to be where you can do single molecule microscopy. Often you can't. There's too much background, or maybe you have a ton of dyes there such that you're not seeing a single molecule. Or let's say you just have regular dyes that are not blinking on and off. I mean, these dyes are very special that, blink on and off. So you don't have it. So in that case, how do you get, or can you get, three-dimensional resolution? Okay? And in general, it's called confocal microscopy. You get the X and the Y, you don't need anything special about, because you look down here and you say, okay, fluorophore is over here, or over here, or over here. Now, but if the sample has Z resolution, Z dimension, that is not so easy to see. Okay. The way you do it is with confocal microscopy. And this is the basic idea. This is your sample over here. It has X, Y, and along here it has some Z dimension. And let's say you have the light that's coming in. Let's say you go here and turn it or something like that. And it goes through this lens. It gets focused down to a diffraction limited spot. And let's say the diffraction limited spot is right here. Then you go and collect the light, let's say through the same objective. If it's a diffraction limited spot here, it goes here. And if this is at the focal length away, it will convert it into parallel rays. Then you take the other lens This is called the objective lens. This is called the imaging lens. You take the imaging lens and you focus it down to a point. And you have some detector. Let's say you don't have this screen with the pinhole here at first. What do you see? When this light is coming down, tell me, where is the fluorescence coming from?
Everything that's in that cone.
Everything that's in this cone. That's right. It's over here, and of course then the light is spreading out. It's all over here, and in fact here and here, because the light is coming in like this, but it's also coming in over here. And so all over here and all over there. In that case, what you're seeing is not any particular z-axis. You're seeing the integration of all of them. Okay? Now, yes? Oh.
I was just, I mean, so we can see on this figure that even the out of focus light, so the teal lines, I mean, a part of that does have to get through the pinhole still, even if it's just a small.
Okay, well, okay. Now we're going to add a pinhole. You've been a little fast. Okay. Now we're going to add a pinhole right here. The pinhole, by definition, allows some of the fluorescent light to get through and hit your detector. But what about over here, or over here, or over here? So, for example, let's just take this point over here. And this point is being excited by the light, and therefore it's also fluorescent. Where, in fact, is this light? Where is it focused to? Yes?
Behind the pinhole sheet 3.
This is going where?
Yeah, right. Back there somewhere.
Yeah, back there somewhere. Okay, but it has to go through the pinhole. Well, how much of that light is going through the pinhole?
Not all of it.
Not all of it, for sure. Most of it is not going through the pinhole. A tiny fraction is going. It's not infinitely good, but only a tiny fraction. So by having a pinhole right here, corresponding to the focal plane right here, that says, by having that pinhole there, you're primarily getting signal from right here. And any other area or volume is not getting through. Yes?
So if it's on that plane, like let's say from our view it's on the one plane, that plane.
Yeah, we're going to call this the z-axis.
Oh, then.
Okay, yeah. So in the same z-axis.
Yeah.
Okay?
Is it gonna look the same in the Like, is it gonna come perfectly into the pinhole?
Ah, good. Okay. Okay, so now let's look at some light that is over here. Where is this light? Let's say it gets excited. Where is this light going to appear on this side, on the detector? Okay, why don't you all figure it out, because you can actually do it if you think about ray optics and so forth. So everybody smiles.
So on this picture, it would be on the the same point, then we just want to pinhole here.
Yeah, that's right. It's in the same plane,
This works,
same way when it's placed upwards, so it's going to focus on, it's going to be in focus at the level of the screen and not.
Other place I use.
I guess
Still should go
which I guess you're saying the sample that
Yeah, exactly right. So any living tissue where you just have big compartments of things, so light beams are going to be altered in ways.
also, don't you have to like know what you're looking at to know whether or not it's like resolved?
Yeah.
You know what I mean?
Yeah.
So that's a good point. We will discuss that. We'll bring it up. Okay. Do we have consensus? Okay. So okay. So we have this here. We have 2 points. One, so they're at the same Z. In one case, right, let's say it's right on the axis. Yeah? So where is that going to be focused? Hello? Yes? No. Yeah?
It should still be focused on the axis at the end.
Okay. Where is it going to be focused? Say this distance, let's call it O.
I guess it should be focused in O distance from its point of initiation on the other side of the objective or lens.
So then you're saying that this is O?
Yes. But that distance away, but still on the axis.
Yeah. Right over here? Does everybody agree with that? Yeah. Yes.
Should we use the formula for the optics like F is 1 over F equal to F?
F is equal to what?
1 over O plus 1 over
Yeah. What is this called? Lens maker equation. That's right. So this has whatever a certain focal length f, and so that's set for the lens, and they have a certain object distance, and then it will be focused, you know, out here. Okay? And what about this guy? This is off axis. How do you determine where this guy will be focused?
Same displacement.
You're saying that this distance, we'll call it x or something like that. So
It's x over something.
why don't you think about it? Talk about it.
I don't know how far
You could either use this, or you can. No, you're not listening.
We're using it
Right, so I think it's the equation we use should be the same, the effective distance should be the same, whatever it should. And effective in the height should be the same. Unless there's something different. Curvature,
just I'm not sure which one. I think it's
For this, we don't even need this equation, although of course it's right. How do we, just looking at this, how do we, yes? Yes, assuming that this is fairly narrow, it's called a simple lens. Any light that goes through the center of the lens just keeps going, a straight line. Similarly, any light that is coming in straight is going to be focused where? At the focal point, which, you know, I don't know. I was saying is here. So, and where these two intersect is where the image of this will be formed. Because everywhere else over here, you know, it forms a big smear. Okay? So in fact, this guy is formed here. This guy always is just formed on the axis. And then, so in fact, if you have an arrow, then you have another arrow that looks like this. Okay. So what happened here? We came in with the lens, and we just use 2 lenses for convenience. And that, let's assume that these are the same. So you comes out, again, right over here. It just goes straight through. Over here, it's bent. That is, this distance is exactly a focal length away. Then any object here, the light will come out. It being at the focal length, it'll be focused at infinity. And then this lens will take it back and refocus it right over here. And so if you have an arrow over here, this guy will be focused as like right over here. And is the pinhole right over here? No, it's not going to hit your detector at all. So you're getting X and Y discrimination. And now what about Z-axis? Let's say you have another arrow over here. Where will this focus over here? Well, it'll either focus, I don't know, either right there or a little bit farther. If I was careful enough, we could figure out which it is. And let's say we had our pinhole such that, over here we want that to get through and nothing else. Pinhole here will get this, and this will, will be all over here. In general, it will not be at that particular point.
What if it's not an arrow, it's a point, and it's in the same axis as the...
Okay, and so you're saying let's not have the Z be different. You're saying let's have the X different?
Let's have the Z different, but let them be in the same axis as the pinhole. On the XY plane.
Okay, Z is this way,
Yeah.
X is this way, and then Y is into the board.
Yeah.
So where do you want it to be?
Like in that diagram,
Mm-hmm.
let's say we just have a point that's to the right of that focal point.
To the right,
Yeah.
okay?
It will still show up as perfect image of the right.
Well, a point here
Oh, no.
will, yes, it will show up right along here, yes, but in general, it won't show up right along this axis. It'll either show up here or there. And if it shows up here, the reason it's showing up there is because there's light converging to that point, and given that the pinhole is really small, only, the amount of area that this passes is this little bit due to the pinhole. So basically, it's discriminating against it. Is it discriminating against it 100%? No. You will still get a little bit from the pinhole going through, but in general, it'll be, you know, the area of this converging compared to the size of the pinhole. And in fact, one of the things that you have to decide is what size pinhole do you want to use? In fact, you can pick lambda over 2. In fact, you can even do somewhat smaller sometimes. What's the advantage or disadvantage of picking lambda over 2 or smaller or bigger? Diffraction? Yeah, go ahead. If you pick a really small hole, your z-axis, in fact your xy axis also, the resolution becomes better because it's discriminating against all other objects. So, okay, let's keep going. Okay, let's get it down really small. What's the problem? Yes, you have essentially a single slit diffraction.
It's going to be hard to find the quality of that.
Yeah.
You don't have enough photons
Yeah. Why not?
because the more you close your hole, less light is coming in.
That's right. Eventually, you close it so much, you know, you keep going, and you're closed, and you see nothing. And so, okay, well, we've gone too far. So then we want to open it up a little bit. Okay, and maybe we see enough photons, so we're happy. Maybe we're not. Maybe we need to open up a little bit more. And that is basically the situation. You have to decide, you know, are you photon starved or are you limited by your Z resolution?
In terms of being photon starved, what is the limit in sample thickness and sample optical density? At what point is there just not enough, is the light coming from the one point just being swallowed up by the rest of the sample?
Yeah, basically what you do is you have to test it.
So, yeah, it depends on what you're using.
Yeah, a question you test it with your various different pinhole sizes. You test it with various amounts of laser power hitting it, and it's really a heuristic sort of thing. And you also, if your sample it has a real lot of fluorescence from here and then from here, then you're tempted to use a narrow pinhole because you're trying to differentiate between them, and you're not so worried about photons coming from it because it's really intense.
So if you did have a bigger sample, what would it look like? It would just be blurry throughout because there wouldn't be enough light coming from the focal plane relative to the rest of the sample?
Yes? Yeah. Let me... Okay, let's just finish this up. In terms of, so what you do is you move wherever you're exciting, you're scanning over here and then over here and then here and then here and here, and then you do it over here and over here. The problem with this is what? your detector pinhole has to move with wherever you're focusing at. And that's true. In general, in this case, you have sort of two pinholes. You have the detection pinhole, and then you have, well, you have to have where effectively your pinhole is in terms of your exciting your molecule. Or, that's one way of doing it. Another way of doing it is you keep this constant, and then you what? You move the sample. And you can do that as well. In fact, oh, and by the way, so this is like, if you have, this is a 3D reconstruction of some fluorescence spheres, and you can get it. There's a problem. Let's talk about photobleaching. Is photobleaching a problem with this? And if so, why? Why is photobleaching a problem?
Because when you're doing all this, the sample is already being fluoresced. So if an area just gets photobleached, you miss that.
Right. So in general, you're focusing down to a spot over here. That's where you're interested. But these guys all over here are also being excited and fluorescing. And the only thing is, you're throwing that away. And so photobleaching is a really serious problem in general. It is the limiting factor in this kind of confocal fluorescence. By the way, there's an interesting aspect. There's something called two-photon microscopy, which potentially gets you around this photobleaching problem. It actually doesn't, but if one person whose name begins with J is going to talk about two-photon microscopy, you can ask him that. Okay. So in this case, these were all sufficiently bright that, it's no problem getting it. Okay. And so you can do wide field, that not coming in with a scanned point that you're going. And then you can do laser scanning, that is, you move it. And this is what it looks like. Hold on. Oh yes. So I'll play this again. This is, you're doing laser scanning. You're going and then you change the focus partly, another z-axis. So that's what you're getting here. In contrast, if you want to do just, wide field, you don't bother to you want to see everything, and then you get on the left, and so you can see this. is all basically discriminating along on the z-axis. Okay?
That one sees that
No, the one there is just the wide field. So you basically come in with your microscope. You're not trying to bring the laser down to a small point. It's wide field, and you end up, you're collecting basically all of the light, including in your so-called field of view, but also at different z-axes. Okay? And so I mentioned that you typically have to have two pinholes. One is there's a pinhole in front of your detector, and then there's another pinhole which is in front of your laser. And it's a real pain in the butt to get them exactly aligned with each other. So, you know, with this pinhole, you're exciting at a certain Z, and you want to make sure you're detecting at the Z. So for this reason, people don't really use this very much. What they use is in general two rotating mirrors, and they have a laser coming in here. It hits off of the one mirror and then a second mirror. Each of these can be turned. Then it goes into the objective. It's formed a diffraction limited spot over here, and then it comes back out and gets through a pinhole and is detected. So remember, in this case, what the detector that you use is just a photomultiplier tube that is, it's not a CCD, it's not an area detector, because you're only interested in that one spot, which is the confocal spot that you get. And these kinds of setups are when you go and you use a laser scanning confocal microscope. And it turns out that you can actually excite not only with one spot, but let's say you have two lasers there, and you excite at two spots, and then you have not one pinhole, but two pinholes there. And not now you can do that. Well, what about three? And what about four? Well, it turns out they have spinning disks right now that have like 100 pinholes. And so what they have is not one pinhole, but a whole bunch of disks. And then they actually have another one to make sure they're exciting with a similar pinhole. And they're in general much faster. It turns out they have certain problems, but whatever.
So the sample doesn't move?
The sample does not move. That's right. You can move the sample. The problem is what? Why don't you want to move the sample in general?
Because if you don't sync it with the computer, it's not going to
Yeah, that's true. You do need to sync it with your computer, but actually, it turns out it's not very hard to do that.
You could also perturb the sample in some way so it's not the same from one
You,
time you move it to the next.
you can do that, or that can happen. There's another reason.
Small drift.
Small drift, yeah, but you know they're pretty good with it. Let's think about, in this case, when the sample is stationary, to move to a new spot, you simply rotate these mirrors such that, you know, it goes in or it goes slightly off and so forth. To move from, you know, let's say hitting here and then hitting a micron here and then a micron here and then a micron here and so forth, you can do that extremely fast. Extremely fast. The corresponding technique would be you don't have any sort of mirrors and you're moving your sample 1 micron, then another micron, other micron. It takes a long time to do that. And it may not seem that big of a deal, but if you're wanting to take, you know, 1,000 spots in one axis and 1,000 spots in another, and now let's say, you know, 1,000 spots in Z. So 1,000 times 1,000 times 1,000. So that's 10 to the 9th. The 10 to the 9th. So if you can move it, you know, let's say it takes, you know, a millisecond to move it, which offhand seems, you know, quite fast. Okay, so that will take you 1,000,000 seconds. Well, I don't know, 1,000,000 seconds is a long time. I don't know what it is. But if you actually can move it, you know, in a matter of, you know, microseconds, then you're doing a lot better. And that's basically why you don't want to have a moving sample. Okay. Yeah.
So is there a limit in resolution that's imposed by the number of mirrors that you have available in this case?
You're talking about the spinning disk now? Well, the advantage of the spinning disk is that you're exciting not just one confocal spot, but 2 or 3 or 100 of them. Is there what is the limit in terms of how many you can have? Is that what you're asking?
Yeah, because I guess imagine on a regular confocal, part of the limit in how well you can image an area is just how small the different movements you can make from one spot to the next are. Or is that not the case?
I don't know. In terms of the scanning disks, as far as I know, they in general do not get quite as good Z resolution as the laser scanning systems. So in that case, you trade off in terms of, you know, Z resolution versus time. And in particular, for thick samples, in particular, the laser scanning is the way to go, that the spinning disk just isn't good enough.